Let's talk about Newton's shell theorem. So Newton's shell theorem has two kind of long descriptions, and then I'll give you the short description. So the two things are that the net gravitational force from any spherical shell or sphere can be calculated as the force from a point mass of equal mass at the center whenever you're outside the shell. So if I'm outside the Earth, I can consider the entire mass of the Earth to be a point mass at its center, and thus find the force of gravity acting on me from the Earth. So at the surface, the gravity is simply the force of gravity, so big G, big M, so the mass of Earth, times my mass, divided by the distance between me and the center of that sphere, so R squared. Now, the second half of the shell theorem says the net gravitational force from a spherical shell is zero when you're anywhere inside that shell. So whenever we're inside of that shell, any mass that's further away from the center than you are produces a net force of zero. And both of these theorems kind of go with the idea that if I'm thinking about these two chunks of mass, let me put a little mark on there for you. So this chunk of mass and this chunk of mass, these two masses, this one's applying a larger gravitational force because it's closer to you, and this gravitational force is going to be smaller because it's further away, but they average out as if I put both of them in the center. And so there's always going to be these symmetric points that are pulling you, away equally. And so all of that symmetry in there actually gets stuff to cancel out, and that's why we can consider it a point mass. Same thing for the outside shell. Everything's pulling you out up above you and away and pulling you down far away, but the stuff pulling you up is closer. So that shell, this mass here is going to be pulling harder than this mass over here. And those also cancel out. So let's go ahead and kind of talk about how this looks when we start to apply gravity at depth or inside these shells. So what you need to think is the only thing that's producing any gravitational force is the mass that's below you, anything you're outside of. Because everything that you're inside of, this entire outer shell, has a net force of zero. And so if I want to calculate my force of gravity here, I'm going to have the force of gravity is equal to big G times the mass. Now this is the mass of this small sphere below me that I'm outside of, so I'm going to call that mr, little r there, times my mass divided by the distance between us squared, little r. Now the problem with this is they typically do tell you at this depth or at this radius from the center, but they don't typically tell you this mass. So we're going to go ahead and put this in terms of the total mass of that object, or that sphere in this case. And so to do that, we're going to start with the idea that mass is equal to density times volume. And for a sphere, density times 4/3 pi r cubed for our volume. Now, if I want to talk about the original mass of my object, it's going to be density times 4/3 pi capital R cubed. And if I want to talk about the mass of my smaller sphere in the middle, it's going to be density times 4/3 pi r cubed with a little r. Now, what's nice here is I can go ahead and I can divide these two equations, and essentially when I divide these two equations, all of this 4/3 pi times density cancels out. So now I have the mass of the original planet divided by the mass of that smaller inner sphere times the radius of the planet divided by the radius of that inner sphere. What I'm going to do here is I'm going to solve for the mass of that inner sphere. So I have mr is going to be capital M r cubed divided by r cubed. And what I'll do is I'll make that substitution here. So now I can say that the force is equal to big G times big M, little m, times there's that r cubed divided by big R cubed, and then we have an r squared here still. That r squared and that r cubed cancel, and we're left with the force of gravity at depth is equal to big G times the mass of the entire object times your mass times the radius of your height above the center divided by the total radius of that object. This is a typical conversion you're going to have to do if you do start to do gravity at depth. Think about trying to find the force of gravity of that inside sphere, because that outside shell, the net force from that outside shell is 0. There you go.